Okay, so let's look at this problem right here. Let me get that down. All right, doing this Fourier transform. So look, when I do this, when I say that this integral is less than infinity, I put here what I mean. So that its Fourier transform is well defined as an integral, meaning that we can just compute its Fourier transform just from the definition and don't have to do any other thing at all, any other more advanced thing than just compute the integral. Compute the integral. There's other things if you could start using distributions rather than L1 functions, or that is functions that satisfy this property right here. Things get different. Okay, so I'm just going to say we compute. This is pretty straightforward once you get the idea of what to do. G of omega. Okay, and I'm going to do the thing that I always do. Which is just to write where the definition is. So it's going to be the integral x going from minus infinity to positive infinity, g of x e to the minus I omega x dx, and then it's like, okay, well, what is g equal to? Just going to copy and paste. What is g of x equal to? Well, g of x is f of lambda x. Like this. So let's save it and make sure that I've got everything looking right. I don't. I forgot the equal sign there. Okay. Now, I want to somehow get a Fourier transform expression for f here. So I need to do u substitution, and I'm going to say u is equal to lambda x. And then what that's going to happen is the variable of integration is going to be the sole argument to f. It'll just be f of u. It'll change the argument up here a little bit. And this trick doesn't always work. Sometimes it puts us into a situation that isn't what we want, but as we will see, this is what we want. So let u equals lambda x, then du equals lambda dx, and the above is, okay, so we're going to have this. Okay, so with the change, with the limits, the changing of the limits of integration, u is going to be equal. So so lambda is greater than 0. So I didn't realize that. So there's not going to be any problem here if x is equal to minus infinity and u is equal to lambda times x. We're going to have the integral going from u equals minus infinity as well. U equals minus infinity. And similarly, the upper limit is going to go to positive infinity. And then f of u, but notice what we're going to have in the exponent here. If u is equal to lambda x, then x is equal to lambda over u. So this is going to be minus I omega u x. Okay, so I'm putting the u under the omega. So, sorry, not, this is lambda, and that's u. So this says that x is equal to u over lambda, but as you will see, it's better to have the lambda go under omega. So the exponent here is omega times u, and that divided by lambda. Whether I put the lambda under the omega or the u, of course, doesn't matter. And this here says that dx is equal to du over lambda. So I'm going to have frac du lambda. Okay, let's see what we have. All right, so now we have this. So what's going to happen? This 1 over lambda is going to come out. And you can put it like with this fraction if you want to, but I'm not going to do that. I'm just going to keep it all together like this, du. Okay, and the reason I'm doing that is because this part right here is going to be the Fourier transform of f, but evaluated at omega over lambda. And so this is going to be, I might change that to a d frac. No, I forgot the f. Good gosh. That's funny. Okay. I forgot the parentheses. Well, Okay, and so that is that. 1 over lambda times f hat of omega over lambda. And by the way, this is what we have in the Fourier transform here. Notice there's absolute values here, and that's what we would get if we assumed that lambda could be negative. I feel like I've done this already, but I don't remember. I think a lot of the problems on this, I've pulled from other homework problems, or they're similar to other homework problems, because this is supposed to be a review. There's another problem as well that I'm not even going to do a Rob Times video for.